Okay. So I I presume that I'll be alone today again. No worries. It's not an issue for me if people cannot join because of work or things like that. If you can watch later the recording, it's fine, and I hope it helps as well. As I said, the last lecture, this will be probably the last lecture because afterwards, of course, we can always dive deeper and deeper and deeper into AI and so on. But I would say that right now, like after watching these AI workshop, the Python workshop, you already have enough tools to start, trying to apply it to your own research and so on. And then by doing so, you will learn with, by doing, so to speak. And I will also continue. Yeah, I'm still here until February in any case. And afterwards, you guys all have my um, LinkedIn, and my email I can share later, my personal email, I mean, because then afterwards we can always talk and I can always help you. And if you're working on a research project and you really want to apply it, I could also even help you and we could even collaborate together. So I would say that for now it is enough to try out. And I encourage you guys to try out because if you never try out, then these workshops are nice for you to know, of course, but then they are not adding a lot of value to our research. And I truly believe that using the AI methods that I taught you, and especially the one that I will teach you today, which is like very, very nice, very new as well. And also using Python to facilitate your workflow and even allow you to using more modern models and so on instead of Excel or other software will also help you improve your research output. So I really encourage you guys to already do it. Um, so this is the last lecture, as I said, but if you guys want me to cover a certain topic that I have not covered yet, or if one of you is interested in another thing, I can always add lectures, like record by myself or invite you and then record so that other people can watch as well. So this is it, I would say. Um, I will share my screen and then we get started with the class because today's class is once again a very, very nice model uh, that you can use for your research that is essentially exploring the power of um, AI and its models, and also using features and methods that we know, in this case from causal inference, causal statistics, to make inference of the things that you are learning. So to not only give you nice predictions, so creating a model that is powerful and is truly representing the world, but also make sense of it to create knowledge and so on. So today we're going to learn about Bayesian causal forests. So a few lectures before, I think two, and also maybe last one we revised as well. We learned about trees, and so decision trees, and also random forests, and also learn how powerful they can be and so on. However, if you do if you perform a random forest, usually you lose the interpretability. And then I even showed you a new model, if I'm not mistaken, it's called explainable. Yeah, maybe I still have it here. Let me have a look. Yeah, explainable boosting machine, which is nice as well. It can give you some, it can give you the importance of the features and so on. However, today we're going to discuss something that not only gives you the importance of the features, but it also gives you possibilities of performing statistical tests to ensure that what you're seeing, so the value that you're seeing, actually makes sense, that you can actually make conclusions based on it. So it doesn't really depend on your data set that you're using or like other random things that could have affected your results, but it's really a conclusion that is true. So you really found a certain pattern there. And this is very, very exciting. I must say that this is based on Bayesian statistics, and well, until nowadays, there are some discussion in the academic world of statistics between frequency statistics and Bayesian statistics. Um, so not everybody accepts this type of statistics. Some people are like criticize it, um, but also there are a lot of people that really enjoy these statistics and really believes that this statistics is robust, which can be. But I will not go further into this, but I just want to let you know that some people are not big fans of Bayesian statistics, but at the same time, there are a lot of people that are big fans of Bayesian statistics, and then truly believe that it can have a great impact on your work. Needless to say, Bayesian statistics is based upon mathematics, proving theorems and things like that. So, uh, yeah, the discussion is not really related to whether it is coherent and robust, but is another discussion that people have. And many people also believe that um, yeah, that there are a lot of people that don't really like Bayesian statistics because it is a bit more complex to perform it instead of the frequency statistics. So it's yeah, but anyways, the model is based on this type of statistics. If you want to learn more, please go ahead. And if you want me to also make a workshop about it, sure, I can always make it. But it would, yeah, it would be like an entire workshop about it, so like a few lectures because it's quite a big topic. But it is also very interesting. Um, and the model that we're going to learn, even though it is based upon like complex theory and things like that, it is very easy to implement and to understand. So that's why we're going to look into it today. But before we start with it, maybe since I mentioned that this type of statistics, the Bayesian statistics, is a bit different than the frequency statistics or the ordinary statistics that we learn when we do like a bachelor, like yeah, when you start learning statistics or just learning the basics. Let me explain what is the biggest difference between frequency statistics and Bayesian statistics. So Bayesian statistics essentially tries to estimate your uncertainty about the parameters that you're trying to estimate. Why do I mean with this? So let's say that we have a linear regression. So y equals beta 0 plus beta 1 times x plus a certain error. And never forget that this error, we call it also noise. And it's like we assume that it's something that you cannot really model. It's just like random stuff that is happening out there. And so your model will never be perfect. We always have some certain error from your predictions. In frequency statistics, as we learned also during the course when I was making like the connection between linear regression and neural networks, and in frequency statistics, to find beta 0 and beta 1, you will simply minimize the uh, absolute, sorry, actually in this case, the squared errors between, oh, my apologies. So you will minimize the squared errors between the actual observations and your estimated observations. So here you will start with a certain beta 1, beta 0. And by the way, with linear regression, you have like a closed form solution. So you don't really need to guess and try to improve over time, try to optimize. But let's say that you would. So you would simply start with a certain beta 0, beta 1, and you try to minimize this quantity here. And this is essentially what the neural networks do, but like they allow for nonlinear relationships and things that are like that. But essentially you are minimizing the error, which could be seen as also, and also there's even another way of estimating this beta 1s, beta 0, which is maximizing the likelihood. which is even has a name, which is like a and I remember the abbreviation, but I forgot what it stands for. I think it's maximum likelihood estimation. Yeah, okay, maximum likelihood estimation, or MLE. And it maximizes the likelihood. And what do I mean with likelihood? I mean like the probability that y is equal to beta 0 plus beta 1 plus, okay, it's a bit more complicated than this, I'm not gonna lie, but essentially it is this. So you're maximizing the probability that what your estimate is what the data is telling you. But in both cases, for the frequency, and this, by the way, is the frequency statistics. In both cases, you will have a value for beta 0. So let's say for this example, 0.5. And you will have a value for beta 1, let's say 1.5. So at the end of the day, you will have this equation here. Okay, with Bayesian statistics, on the other hand, what we will do is we also gonna maximize the likelihood. So we will use okay, we use what we call like the Bayesian maximum likelihood estimation. But I'm not going to discuss this into this because it requires quite some mathematics. But essentially, we will also focus on maximizing the likelihood, so the maximizing the probability that y equals what your model. But in this case, we will consider the beta 0 and beta 1 as what we call random variables. And random variables are variables that follow a certain distribution. So in this case, we could say that beta 1 follows a normal distribution with mean 0.5 and standard deviation, let's say 1. So this will be our beta 0, or actually our initial guess for beta 0. And this, what I'm plotting here, is what we call the prior prior estimation, prior distribution of beta 0. And with beta 1, let's also do the same. So let's say it's like a 1.5 the mean, and the standard deviation of the normal distribution is 1. And by the way, it doesn't necessarily need to be the normal distribution. It could be other distributions as well. And then also the prior for beta 1 is here 1.5. And so essentially what you're saying is like, you're saying like this. So I know that the value for beta 0 and the value for beta 1 should be like around 0.5 for beta 0 and 1.5 for beta 1. But it could like vary a bit between it. But in any case, it will not be, for example, for the beta 1, you will very, very certainly not be minus minus 2 or 5. And and this is because like with the likelihoods of the normal distribution, that you have like, if I remember correctly, the mean plus or minus 3.5 standard deviations. Like this range here is the range for the 19 90.7%. So 99%, like you are 99.7% confident that the values are between -2 and 5. And if you would guess, you would say 1.5. And then, so you have these prior distributions, and then you're gonna have your model, which is like a beta 0 plus beta 1 and x, and then you give it some data to it, and then you estimate what we call the posterior distribution. And we to estimate the posterior distribution, by the way, we use what we call the Bayes theorem, which I will not explain now because it requires some math, but essentially, like, it is trying to improve these distributions here, giving your data. So giving that you see your data and have seen like the performance of your model, and like all the possible values for beta 0 and beta 1, and also all the possible interactions between them and so on. Like, given this, you can also estimate improve your guesses for the distribution. And then let's see how it is right now, the guess for beta 1. It is still 0.5 because this is the real value, and this is the value that you would get for the frequency estimation. And here as well, it is 1.5. However, right now, so the beta 0 is still following normal distribution with 0.5, but right now the standard deviation is also 0.5. And the beta 1 here, same thing. So it's still normal distribution with mean 1.5, but standard deviation is 0.5. So right now, these limits here of our confidence are smaller than the prior one, because right now we have the data, so we are more confident that beta 1 is in this region here. However, we still believe that there is the possibility that, so 1.5 minus 3.5, and the standard deviation, so it is the square root of oh, okay, actually, since here I'm giving the standard deviation and not the variance, let's put 0.25, so times 0.25, and then, yeah, actually, let me even use the calculator because yeah, because nowadays I don't really make a lot of calculations by head. Okay, so here's gonna be 0.625, and here it's gonna be 2.37. So right now, like, we are much more confident of where beta 1 is lying, but we're still allowing for some uncertainty. And it is essentially what Bayesian statistics is. So you are considering the parameters as also random stuff that you don't really know, and you will never know for sure. And so that's why we are using distributions to know more or less where it should lie. But they are like, when you do a t-statistics, by the way, for the beta 1 and beta 0 with the linear regression that I think everybody here have already done one day in their life, you are also assuming more or less that beta 1 follows a normal distribution. And then, like, you have your certain mean, and here you're gonna have your standard error, and then you will do like the t-statistics. By the way, yeah, it is like that, and then you will estimate your p-value, and then you will give how confident you are about it. So, and this will give you more or less, yeah, how confident you are. So confidence interval, and you could think that this is quite similar as this one here. So the narrower this thing here is, this where the lower your p-value will be. And for example, let's say that we are testing whether your coefficient is like above zero and not zero, so that your coefficient really exists, so to speak. Then in this case here, like to go to zero here, I think is like maybe you will need 4 or even 5 standard deviations. So the p-value here will be like very, very small. So it'll be something like that, more or less. And yeah, you would get the p-value, like this very small p-value for the frequency approach. And for this approach here, you can simply estimate the p-value with the distribution. So like they are connected to each other in a certain way. Okay, now that we know what Bayesian statistics is more or less, we're gonna have a look at this model called Bayesian Causal Forests, which once again make use of random forests, and it will give you the importance, so the coefficient for the variable that you want to, the explanatory variable that you want to study. And it will also allow you to estimate a certain p-value, as I said, as I told you here. So it will give you at the end this distribution here, this distribution here, and then you will be able to estimate, for example, what is the probability that the beta 0 given this distribution is like above 0, or actually in this one, the beta 1, the probability that the beta 1 is above 0, and then you can estimate your probability. And in this case, it is virtually 100%. In this case here, I think, so let's even do the math. And by the way, let's maintain here 0.5. So here, this is right now 1.25, and this is 2.20. So we are kind of confident that it is above 0. However, let's even do with 1 standard deviation. So okay, so with 1 standard deviation will be here 0. So if you would do here with the p-value and so on, you would probably get a p-value which is like approximately let me even do the math. It would be probably like something close to 50%. So it's like, yeah, like this p-value is a bit too big. So your confidence here is like, yeah, and usually the confidence you could approximate by 1 minus the p-value. So your confidence here that this beta 0 is actually like meaningful. So it's like you're like the 0.5 is actually meaningful, and it's not that it could be like a positive or negative, so you don't really know what is happening. It is only 50%, which is quite low. So in this case, you would probably reject the hypothesis that this beta 0 is yeah, statistically significant. Okay, so how does this model work? So to explain it, we're gonna use some notation. So the y would be the what we call in causal statistics the response variable, but it's essentially the target variable, so the variable that you are studying. And in this case, let's assume that this is like firm's profitability. Okay, the z variable here would be the variable And in the original paper, it was only for binary variables, but right now you can also use with continuous and even categorical variables. But it's essentially the variable that you are studying. So in our case, and let's make binary to make it easier for the example. So let's make this, for example, ESG investment. So like if z equals 0, if z equals 1, it means that the company is performing ESG investments, and we can even assume like that it is performing, like, I don't know, with a certain percentage of their assets or something like that. And if not, then it will be 0. So this could be a proxy for like how concerned and how focused the company is on ESG and sustainability. And this X here, which is a N by D matrix of control variables. And by the way, N is the number of observations, it is the number of control variables. These are essentially the variables that we already know beforehand that are important to estimate Y. So in this case, for the firm's profitability, probably is like firm's size, and also the past profits, maybe even, I don't know, the market share, anything that it is important here. And the more the better in this case, because like, or of course you need to add things that you are sure that are important for the Y. So if you start adding random stuff, this could also mess up your model. So but there are the control variables, so the things that we already know for sure that are important, and in many cases you already know what is important. You are studying like a new thing that could be important, in our case ESG or sustainability and so on. Okay, so whenever I say Y, it is what the target variable. So what, like the thing that we are studying to make a relationship with the Z, which is like the explanatory variable that we are studying, in this case ESG investment. So if the company really invests heavily or not in ESG. And the X are simply the control variables, so the variables that I already know that are important. And why do we need the control variables? Because if we don't have the control variables, and let's assume also that the Z variable, so the ESG investment, is related to some of the control variables, so they have a certain correlation, then probably the coefficient that you will get for the Z variable will be higher than in reality. And then in this case, you will probably say, oh, the Z variables is very important, but should you have added the X variables, then maybe you would see the actually the Z variable is not important because the other X variables already are enough to estimate the Y. So they already explain the variation in the Y enough. Okay. Now, so what we want to estimate is this, what we are calling tau. And by the way, whenever I write something, for example, in tau or f, and I put in brackets another thing here, it means like that it depends. So tau depends on xy. So the variables of tau depends on xy. So in this case here, we are estimating what we call the conditional average treatment effect, which is also notation for the for causal statistics, but this is essentially your coefficient. And since I'm writing here conditional, it also means that like your coefficient will depend on the axis that you're considering. So for a linear regression, you can think that you will have like you have your data, and to make it more like to make it to make it like more robust, your estimations, you also divide your data set that for, like, let's say you have a lot of firms, you also divide them into like developing and developed countries, because maybe the coefficients there, so the relationships there are different. Or you could also be based on the size of the company, or even both as well. So the conditional average treatment will also depend on the axis. So if so in this case, we're going to have like a coefficient for each, and this coefficient will depend on the company, which makes sense, or for example, the size of the company in this case, which makes sense because it, for example, yes, is in this case, we are trying to see if ESG investments are important for firms' profitability, and if it has a positive or a negative correlation with it. And probably for small firms, the ESG investments are up until right now, or up until a few years like in the past, it was not important to a great extent to small companies. Because small companies, first of all, if they invest in ESG, so in make their things more sustainable and so on, it will cost them money as it costs for the big firms. But if they don't invest, it won't cost them money, and probably there will probably not be any boycotts from customers or anything like that, because some like these small firms, sometimes they don't even have a brand. Sometimes they sell directly to a supermarket, which will sell based with their brand. So so here you could think of like small suppliers that sell, for example, produce waffles and sell them to Albertine, and then later Albertine sell them as if it was an Albertine product. So in this case, it will not make sense for this company to invest in ESG, because investing or not, it doesn't really have a big impact on their profitability. And if they invest, it is even negative. So in this case, you have a certain relationship. Um, and in another case, when the firm is like very big, then investing in ESG would probably have a positive impact on the firm profitability. Because if they don't invest, then probably right now it's already happening, in the future will happen more and more. People will stop buying their products. Maybe they will even get some fines and things like that. So in this case, it does make sense to use this conditional average treatment effect. But if you believe that, or if you just want to estimate the average relationship, then you're going to use the ATE, which is essentially average treatment effect. And in this case here, instead of having the XY, so instead of depending on X, it will not depend on anything. So it will just be a tau here. But the equation here will be the same. And okay, so here we are dealing with in statistics what we call expected values, but essentially it's like essentially yeah, instead of reading as expected value, you can read the mean, so the average. So here's like the average of y given that given xy here, so given the control variables, and given that the z y equals 1. So given that the thing that you are studying here, in this case ESG investment, is present in this case, and if zy equals 0, means that this ESG investment here is not present. And the difference between these two here would be the condition, the condition average treatment effect, or even the average treatment effect. So this is essentially at the end of the day what we want to have. And since we are using Bayesian statistics, actually at the end of the day, we're going to have a distribution for tau. And assuming that tau follows a normal distribution, we will have like something like this with a certain mean and a certain standard deviation. And then given the mean and the standard deviation, we can start estimate p-values or confidence values for like example, and we're gonna see this later, for like what is the probability that tau is greater than 0. So let's say that tau is indeed greater than 0 here for the mu. So let's say it's like 2, and the standard deviation here is 0.5, let's say. And then you can estimate the probability that tau is greater than 0. And then you do this with the normal distribution things of like this CDF, PDF, and this is not that difficult to do, and many softwares can do directly for you. But in any case, well, the most important thing that I want you guys to know is that because we are using this Bayesian statistics, we're going to have a distribution for your conditional average treatment effect, or like you can read this tau as like the coefficient. So for the linear regression, this will be the coefficient. And since you're going to have a distribution, and you will know the distribution and also the parameters of the distribution, you will be able to estimate such probabilities, and you will be able to like estimate how confident you are that a certain relationship is positive or negative, which is very nice, and something that we are all trying to achieve. And if you can do this with like a strong model like random forests, then not only you will have this possibility of giving a certain probability for how confident you are, but you're also going to have a strong model that you can base upon this probability. And the stronger the model, the higher the likelihood is that your probabilities at the end are the true probabilities and not like crazy probabilities that came out of nowhere. Okay, so in any case, like whenever you're trying to estimate something, you will have your y here, and then for the ith firm in this case, you have your observation here, so the yi, and this will always be equal to a certain function here, which depends on the xi and the zi, so the control variables and whether the company is heavily investing in ESG or not. And it will always have a certain error here. And in this case, we're assuming that the error or the noise follows a normal distribution, which is like a quite standard, of course. One thing that is important to notice before I continue explaining this is that the model that we're using here assumes that the studied explanatory variable that you're trying to study has a linear relationship with y. So for the control variables, not necessarily have a linear relationship, and this is what makes the model so powerful. But for the z variable, the variable that you're actually studying, you are assuming that it has a linear relationship. This is good because when you're talking about conditional average treatment effects, or when I talk about the coefficients, if the relationship is positive or negative, you're always thinking of a linear relationship. So usually, it makes sense to make this assumption, even though it might not be the true assumption, but it makes easier to interpret your results and so on. But it's also bad because there is a possibility that the variable that you are studying does not have a linear relationship, but maybe a quadratic relationship, or a cubic relationship, or a cosine relationship, a sine relationship. So yeah, there are many other possibilities. And then it's like, okay, it would be nice to also not make an assumption that of this linear relationship, so not assume anything. But up until right now, we don't really have a model that does this. Or actually, we do have such models, but they are not interpretable. And when we apply some methods to make them interpretable, usually we don't really have the possibility of getting a distribution and estimating p-values. So this is the best, this, as far as I know, of course, this is the best that we have for now. But okay, so let's come back here. So here I'm using the expected value to not write again the the error here, but you can think that this whole thing here of the expected value of yi given the xi and the zy, this is the same as writing the function yi, or actually the estimated. My apologies. I messed it up. So this is the same as writing the like a fx I and zi, so like a certain function that it could be anything plus the error, which is what you're trying. So this will be your model, what you're trying to estimate, plus a certain error. So yeah, we just write this e here to say like, okay, we are not considering the error. Okay, but your estimated yi will be equal to this me or mu, depends on how you pronounce it, but it is like a Greek word, and but you can ignore for now. Essentially, this whole thing here is a function. So it's a function that depends on the xy, so the control variables, and this pi hat xy, which is also another function that depends on xy. And this pi hat xy here is what we call in causal statistics the propensity score. It has a bit of a crazy name, but it's very simple. It's the probability that zy equals 1 given xy. So what I mean, this is in this case, the example that we're using, this pi hat xy is the probability that a company invests heavily in ESG given the control variable, so given its size, country, and things like that. This is very important because these will take into account the possible biases that you have in your data. So for example, if you don't take this into account and you just train like a random model, you could conclude, for example, that the countries from developed, or sorry, the firms from developed countries are willing to invest in ESG, while the companies in developing countries are not willing to invest in ESG. So you could conclude this, which we all know that's not true. And it's probably because, and actually it's very, very likely that this is the case, because the countries in developed, the firms in developed countries possess more money, usually, like free cash, and they usually have more subsidies that they can profit from. They have usually also easier access to credit. So they have a lot of other factors that make it easier for them to invest in ESG. While for the developing countries, this is not the case. So by adding this, what we call propensity score, you will take these possible correlations between what you're trying to study, so in this case the z variable, which is the ESG investment, and the control variables, and this will allow you to not to avoid these wrong conclusions that sometimes we can have. So okay, so you have a function that will depend on this propensity score and will depend on the control variables, and this will be like our main function, so to speak. And then you will have this other thing here, which is the most important thing here, which is like a certain value that it will estimate. So is the tau xy. So in this case will be the conditional average treatment effect, but it could also simply be tau and here times cy. If you don't believe that the relationship depends on xy, so if you believe that the relationship is equal to all the other things, and we call this like a homogeneous relationship, while the other one, it will be a heterogeneous relationship. But in any case, it will be a certain number that we want to estimate once again. and actually we're gonna estimate even this whole distribution times the ZY, and the ZY will be 1 if the company is investing heavily in ESG, or 0 otherwise. So by doing like that, you have construct a model, and since this first function here, so the mu xy and pi head to xy, since they are both like they can be both nonlinear, they can be any function, to be honest. And in this case, we're gonna estimate this function with this Bayesian causal force. So with the strong random force, so we have a strong performance. So we'll try to extract the most amount of information that we can from the data to estimate the yi. And if there is any other information that we are not being able to estimate from the control variables, but we can estimate from the z variable, this will be the additional information that we're going to use to make conclusions. And if this extra information is there, you will be able to conclude that in this case, the ESG investments are important for the firm's profitability. And given the distribution that we will get here, you will be able to say whether this relationship is positive or negative, and like what is the probability that it is positive and what is the probability that it is negative. So this is something very, very powerful, and once again, that you guys can use in your research to construct knowledge. And not only create models that predict things, but also learn about the world with your models. Okay, so now, so let's see how we're going to estimate this mu xy p hat to xy. So to estimate it, we're going to use what we call, it's called Bayesian additive random. Okay, no, I forgot. I remember the I remember the name. Okay, yeah. So it is actually the it's called Bayesian additive regression trees. So or BART. It's also normally said as BART, but it's not that difficult to understand how it works. And since we saw already random forest, I think it will be quite easy to understand this. So essentially, it will be a random forest. So you have a lot of trees, and each tree, we're going to try to make it quite shallow, so not very deep, to avoid overfitting. So yeah, we say that each tree will be like a weak learner, and I even wrote here like weak learner. And then we're gonna, as we learned last time, like we're gonna use the explanatory variables to create some rules to split the data. And yeah, how we make the splits, yeah, it depends on what you choose, but usually it is like each split will try to decrease, like yeah, it would be like as if you would stop after the split, and then you would try to decrease the error that you would get between your predicted values and the actual values. And by doing this, you construct the splits, and then you have a lot of trees. Usually those trees will use different explanatory variables, and sometimes they even use interactions between these explanatory variables. And here it could even be like a x1 and then square it, or even cubic, or yeah, it could be here like how to determine the split. It doesn't really have any limitations, like it can be any rule that you think of. And you have a lot of trees, and how we will make use of these trees. So every time you have a certain output for each tree, and then we're going to assume that the yi equals f of xy plus a certain error, and this f of xy is estimated by summing the output of each tree. So the output of each tree will not be the prediction for the y itself, but it'll be like a partial prediction. And when you sum all these partial predictions, you get your real prediction for the target variable, in this case, the y here. So you simply get a lot of outcomes here for each tree, and each trying to learn a certain different information for the variable, and then you will sum out the information to get your prediction. Okay, so this is what we learn as random forests, and okay, yeah, this is what we learned from the random forest, so it should be only revision up until right now. But what BART will do differently is that, first of all, it will make use of this function here, which is the probability that a node at the depth h splits or not. So to determine whether it should split or not. So remember last time we saw like some possible rules that you can use to determine whether the split should continue or not. In this case, we are also having such a rule in this case. And these values here are the values that people usually use. So it's like the standard for this model. But okay, so after I have created this random forest here, using this rule here to see whether it go further or not, what you will do, you will perform the same procedure once again, and using this estimated random forest here. But then for each tree, you will perturb it a bit. And how can you perturb? So for example, you could change a certain value here. So for example, before it was, the rule was if x1 is lower than 0.8, and here this case is if x1 is below 0.75. You could also get rid of splits, or even add splits where it didn't have. So for example, here and then here, and even like use different variables that you use in a certain tree to other trees and so on. So you're just gonna make some small perturbations for each tree, so change it a bit, and then you will do this quite some times, and then you have like your, in this case, like the f1xy, which is like your first random forest, and actually the output for it, so this fxy here, so your prediction for the y for the first random forest. But then you also have like other ones here that are smaller than the one that you got, and other ones here that are higher than the one that you got, and then you will simply get all these possible predictions for the y, and then you will more or less create a distribution of them. So of course, this first one here that you estimated as the random forest will be the one that you would go for. So this will be the mean, will be the one with the highest probability of being true. And the other ones, yeah, depending on where they lie, they could be like here, 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 or here, here, here. And you estimate it based on the outcomes that you have. But like you don't need to focus a lot on this procedure and so on. What I want you to really know is that at the end of this procedure, we will have a certain distribution here for the estimated fxy's. And then you can think that this estimated fxy will be equal to this mu xy plus tau xy if you were using the conditional average treatment effect, times cy. And if you want, and you actually should also add for this mu xy, you should add the propensity score. And this mu here, the function of the mu would be the BART, so it will be estimated with the BART model. And this tau here, zy, will be estimated, it could also be estimated with BART or any other way that you wish. But okay, so once you have done it, all this procedure, you will get your, once again, your distribution for tau, and it can even be your distribution for tau xy. So given your xy's, you're gonna have a certain value for tau and its distribution. And then let's have a look at the results of the paper soon. Before, let me just show you how the propensity score can be important. So in this case, we have a propensity score, we know already that there is a certain relationship. But if you would not know, if you plot this, you would kind of understand that there is a certain relationship between the mu, so what you're trying to estimate of the function here, and the propensity score. So in this case, it would probably make sense to go to the second one here. But if you would be completely random here, then maybe you can forget about the propensity score. I would say that in any case, it makes sense to add the propensity score for your BART model here. Okay, now is the time to look at the results of the paper. So this is with simulated data, but we're also going to have a look at real data. So here they compare the BCF, what we are learning today, Bayesian Causal Forests, with like some other models. So in this case, some BART models, or even causal random forest that we have not learned, of course, or even here a linear model, so like a linear regression, plus a certain shrinkage method that they have to make this linear regression even more powerful. And here you have the average treatment effect and the conditional average treatment effect. And this is it the case if it is homogeneous. So if it would make sense to use only the average treatment effect, or heterogeneous if it would make sense to only use the conditional average treatment effect. Let's have a look here. Okay, so the RMSE will be the error between like the estimated average treatment effect and the real average treatment effect. And as you can see, this BCF is better than all the other machine learning models, but is not better than the linear regression one. And this is also the case here. Even when you are having more like samples. So the difference right now between the linear model and the BCF is a bit lower, but it is still the case. Cover LN. Okay, so cover is like the coverage of the model, so of the distribution that is giving. And yeah, if I remember correctly, it should always be here 95%. So yeah, BCF here is not always the best one, but this one is also important because this one also takes into account the length of your interval. So in the sense, like if you have like a very big interval here, okay, sorry. If I remember correctly, maybe okay. Yeah, okay. No, I remember it correctly. So here should be 0.95, and the length here will be like the average length that you're having for. So let's say here you have a certain prediction, and if you also have like other, like if you create like a distribution like this, it's okay. So now I'm gonna explain. So let's say that your real predictions here, your estimated is here, and these are the all other possible values that your model is giving, and with the different probabilities, of course. The coverage is essentially how often this red thing here, so the actual value, the actual observed value, is within 95% of your distribution, and the length is more or less how wide it is. And of course, the wider you make, the easier it is for the real observation to be within your estimation of the possible distribution. So long, uh, long story short, the length here, the lower it is, the better. And the cover here, the closer it is to 95%, the better. Okay, so in this case, for the average treatment effect, as we can see, that linear model is actually better than the other ones, and but as an increase, this difference decreased to some extent. And when you have an heterogeneous effect, um, so actually they made a poor work with the table. So to make it easier here. So with heterogeneous effect, the ATE here, like, which in my opinion don't really make a lot of sense to look at it. Let's look more at the CATs. So yeah, then it just makes sense that the conditional average treatment effect here. Okay, in this case here, once again, the linear model is much better, and even when an increases linear model is still better, even though the relative difference between them decreases a bit. But okay, so now you're maybe wondering, like, why would I ever use any of the neural network models to estimate? And by the way, this, we're not talking about the error of the predictions, because the predictions from the machine learned models are certainly better than the ones from the linear model. We are talking about the error between the coefficient of the variable that you are studying. So actually what you want to know, like the relationship between the y, so the target variable, and the explanatory variable that you are studying. Okay, being said that, as you can see here, the linear model is usually better, so it will not make sense to use what I have just shown you guys. But this is for when the uh, data generating process, so DGP, is a linear model. So if your model is linear, yeah, then please go ahead and use the linear model, because it will always give you better results, as they have proven here. But the reality is that usually in the world, most things that we study, most phenomena that we study, are nonlinear. And in this case, and as we can see here in this table here right now, it makes more sense to use the machine learning methods, because as you can see right now, the linear models are very, very bad. And then the machine learners are much better. And from the machine learning models, the BCF is always the best one, both with homogeneous effect as well as with the conditional average treatment effect. Okay, so I hope that I hope that I have convinced you guys that the BCF really can really be beneficial, especially when you believe that what you're studying can have a nonlinear relationship with one of the control variables. So yeah, and usually this is the case. So for example, profitability of the company, yeah, the size is certainly important for the profitability, but usually the size, maybe at some point it is a linear relationship, but maybe at some point it becomes quadratic, or even some point it becomes even negative. Uh, and this is also with many other things. So yeah, if you believe that one of the things on one of the control variables that you are studying have a nonlinear relationship, please use the BCF. If you are certain that all the control variables that you are studying have a linear relationship, please don't use it. Okay, now it is about, and this one is with continuous variables that we have not seen today because it requires a bit more of math, but the concept is almost identical, and it is they are doing a study about the effect of abortion on murder rate. And yeah, this is like was initially proposed by this very famous study here, and saying that like there is a negative relationship between abortion and murder rate, and they perform like a robust linear estimation, blah blah. And then other people were not agreeing with it, and then they performed other linear estimations, but then they used different control variables, and that they even got like a positive relationship. So it was a lot of debate. So what they did is they redone this study, so using the same data set, but now using, in this case, the BCF, both estimating that there is a certain homogeneous effect or a certain heterogeneous effect. And here we can see the probabilities of the estimated tau. Okay, so the original paper got, if I remember correctly, here would be like minus 0.12 for the coefficient, so for the beta. And then you had like a certain standard error. So in this case, you can even create a normal distribution based on it. And then you had like a p-value here, as you can see, is quite far from zero. So you had like a significant p-value and so on. And this other one will be like even a newer way of doing linear modeling. And as you can see, is also close by, and even um, and it even gives more certainty that it is negative. But if in both cases, you could always say that, hey, but maybe there are some things that are non-linear, so these results could be biased and so on. So as you can see here, assume that it's non-linear, so assume that only these two models here, so the um, purple and the orange ones are relevant. As you can see here, they give you these distributions as well. And you can see here that there is much more uncertainty than the other ones, which is probably, yeah, which probably shows that this model is really representing reality well, because, yeah, I mean, those things are very complicated. They have a lot of non-linear relationships, and probably you're never going to have enough control variables to really estimate it for sure. So it makes more sense to have like a quite some uncertainty in your estimation. So that's why you have more certainty. However, they do give you a tau that is, for example, let's focus on the homogeneous one here. They do give a tau here, which is like 0.19. So it's like negative 0.19. So it's even higher than the one given by this one. And when you perform, so but the p-value is quite similar than the other one. So in any case, they found that there is a negative relationship between abortion and murder rate, and there is like a, yeah, you have like a significant p-value, so you can be quite confident that this is indeed the case. But whether this is minus 0.19, or even here in this case, okay, let's say this one minus 0.3, or even here like minus 0.05, whether it is this one, the other one, or this one, yeah, you don't really know, and you're never gonna know. But if you need to guess, you guess this one, and it's very probably that is around this one here, and not all the way here to minus 0.5. Okay, so this is something that you guys could do your own research, and maybe you have like such a graph like that, and then you make such analysis. Is much better than what we usually do, that we just do the coefficient estimation and give the p-value, say like, hey, we are certain about it. Here we actually can visualize and see like how, okay, we are, like here in this case, we are certain that there is a negative relationship, but we also showing how certain we are that this negative relationship has this order of negative 0.19, or it is, yeah, maybe a bit lower or a bit higher. So I think like I really like this way of analyzing your conclusions and so on. And here, so here is using the conditional treatment effect, and it is conditioning on the state. So one of the conditional variables is the state where your data is. And as you can see here, if you consider, so this uh, value here is the value, so is negative 0.19, which is like the average treatment effect that we got. Um, However, if we only consider Texas, we can see, look, that we are much more certain that there is a negative relationship, and this negative relationship is almost even minus 0.3. Whereas if you consider something like, in this case here, I think it's Kansas, and there is even a positive relationship, like a very small positive relationship. However, it could be positive, could be negative. So here probably the p-value is like quite high. So your confidence, which is always 1 minus the p-value, will be quite low here. And in this case, you will probably not say that abortion has a negative, or even that abortion has like a significant relationship between murder rate. It could have, because but with the data that we have, we can already say this with certainty. And as you can see here, sometimes it is symmetric, the distribution, or like yeah, of the estimated relationship, but sometimes it is asymmetric, like in this case here. So we are also considering possibilities of having this tau here, which does not follow a normal distribution, which can also be true. Like not everything in the world follows a normal distribution. And by the way, yeah, I don't even like to say normal distribution, because the actual name of this distribution is the Gaussian distribution, and it was discovered for errors. And okay, sure, you have the central limit theorem and things like that, but you have some assumptions from the central limit theorem. So long story short, not everything follows a normal distribution in the world. And in this case, we are also exploring this possibility. And we are having here, once again, much better results than what we would have with like the standard linear regression that we usually do. So this would also add a lot of value for your research when analyzing. And here, instead of state, we do have countries, or we can even have like firm size, or yeah, many other things, and explore these things and see like what are the relationships, like even this, like what is the possible relationship between investing SG and so on. And so I hope that I have encouraged you guys or motivated you guys um, to use this for your research, because it's a very, very nice thing. And I will end the class with showing some code of how to implement it. But once again, if you are very interested in doing this and you don't want to spend a lot of time learning how to code it and so on, please let me know. We can work together. And yes, but yeah, I mean, the code that I found that code in Python. So once again, it's a very, very new thing. So you don't really have a lot of, unfortunately, you don't really have a lot of, okay, let me search what it was. Yeah. Okay, now coming back, we don't really have a lot of libraries, like Python library or R libraries for it. The only ones that I really know are these ones here that I'm showing you, and the ones that are actually, so okay, this is sparse BCF and this flex BCF. They are new, or targets move. They are new things, so new models. So it's not necessarily they are the models that we learned today. That's I want to make clear. But the two ones that I know for sure, because okay, this guy I know him personally. Uh, okay, not that I saw him personally, but I know him, like I've already spoken with him and so on. And then this one here, which I found today, and I looked at the code, and it is indeed what I have taught you guys. These two libraries are really implemented what I have just taught you. And this one here, the person even made the code available for Python, but when I tried it out, unfortunately there was one problem with their code. So in this case here, so I already told them and asked them to modify the code accordingly. I will wait a week. If they don't do it, then I will probably copy their code and modify it and then make available for you guys if you guys want to use it. But then yeah, but here you would probably have this. But now let's have a look at the R. And now, by the way, I used also from this guy. It's R, and I think, okay, I don't know if it is a man or a woman, so I was gonna say their code. Okay, so here we're gonna generate 50,000 observations, and then yeah, okay, we're gonna make like give some distributions for the the controlled variables, and also we're gonna make a tau here, and this tau, as you can see, depends on x4 and x5, so it depends on certain control variables. So it is here will make sense to use the conditional average treatment effect. And here we have a certain mu that we are using, which is also complicated and like it's a complicated function. The pi here, which is the propensity score, and in this case we already know what it is, but in yeah, if we didn't know, we would try to estimate it, of course. And then the z variable here, which is a binary variable, so it's 0 or 1, but it could be continuous, and it also has the code for continuous examples. Okay, and then we also generate the data that we are trying to estimate and so on. And then here we prepare the data to be able to use it for the model. And here's where we run this BCF, and here we have like a certain x, and it comes from accelerated, because there are also some ways to perform the estimation of the Bayesian causal force a bit faster. But okay, but then here, as you can see, it's not a lot of coding. Like this here, there's a lot of code is more to generate the data. But if you already have the data and you want to run it here, as you can see, it's not a lot. Okay, it is not in Python, it is in R. So if you don't know R, it can be quite confusing. But I mean, in theory, you just copy and paste, and then you just change the data. But as long as the data that you have is in the format that it needs, it will be fine. Okay, and then you will estimate the tau here, so that you will get the tau heads. And here it is plural, because yeah, it will depend on the axis, because we are talking about a conditional average treatment effect. And then let's have a look here at the results. So well, as you can see, to do the estimation for 50,000 observations, it took me 46 seconds. And our average error between the estimated taus and the real taus, and once again, remember that there are many taus because they depend on the control variables, is 0.064. So it's not a big difference. Also given the giving the magnitude of the tau that we have. And here we are plotting the real relationship, or actually, sorry, we are plotting the real tau here, and how tau changes with the axis. And as you can see here with the line, it is the line here will be the real tau, and the tau head, so the estimated tau, will be these circles here. And as you can see in the extreme values, it starts getting quite wrong. But in the more middle variables, so when the tau is not that big or not that small, then it gets the values quite accurately. So yeah, and also you could also perform these graphs here that I showed you to see the distribution of the taus and so on. I have not done it here because I still need to learn a bit more about this library, but I can do it later and send to you guys if you guys want. But essentially this is it. So, and if you would do by yourself, you can ask for my help, of course, but essentially you would run the same code here as this one here. You would just change the y, the z, the x con, and okay, x con and x mod. These are the same in this case, so simply are the control variables. The pi hat you will probably estimate, and I can later show you how to estimate. And there is even Python code here when I was trying the other one that shows how to estimate the pi hat. And yeah, and then you also have other things that you can change, but yeah, and you can play with it, of course. Like these are the so-called hyperparameters, but yeah, I would say for to start, you don't really need to play with them. And then the only thing that you need to do is once again replace the data, but the code remains the same, and you don't need to write a lot of code, and you can get such a graph like this for your research and other graphs that I will later look how you can do, like this one and this one, which once again can be very, very nice. Okay, so of course I will share this code here with you guys and maybe even add some code to it and to try other plots and so on. But once again, so it took me 46 seconds for 50,000 observations. Probably not gonna have a lot of these, right? So I remember, if I remember correctly, I also tried in the first time with 5,000, and it took me 0. Yeah, it took me 6 seconds, sorry, not 0, but 6 seconds. So it's super fast as well. So this is also something very nice. Yeah, this is it. This is our last lecture. I hope you guys are now quite excited to try by yourselves or even try with my help for your own research. And of course, there are other models out there, and there are always more things that we can learn and so on. But then, yeah, it starts to become quite very specific. Your mathematical knowledge, it starts to be required. So I would also need to teach you guys some mathematical things to really understand the models. And sometimes you would even need to discuss models that are still like, they have been already published but not very extensively tested. So then becomes also like, yeah, then it already becomes a research, so to speak, that we could try these models and so on. And so I would say that for now you guys already know enough, and I planned this course to end like this so that you guys have like a clear model that I believe has a lot of potential, and there is not many studies use this model. There's one study that uses this model that is very, very famous that I can just share with you guys, that was published in Nature. Was about like positive feedback, and it's used in poor poor schools from America. They have like a poor population, and how this had like a positive impact in their grade and so on. So it's also a very nice study, and I will share after the lesson. But besides this, there are not other many research, especially social science, using this. So there's a big opportunity for you guys to try it out. And even if your research idea is not super innovative, since you're using a very innovative model, it's already a very strong quality from your paper that you can use to increase its chance of getting published and so on. Thank you for your time, for your patience. And once again, if you guys want anything extra or any new workshops or anything like that, just let me know. But for now, this was it, and we see each other soon. Okay, bye bye.